Ladies and gentlemen, ears open, eyes wide. We're going to get started here. Welcome back. So, on tap for today, we'll continue on with the story about resonance and making sure that we are okay with drawing out resonance forms. And yeah, we'll see where the wind takes us. So, recall from last time we had talked briefly about how the resonance itself, right? The whole importance of resonance, at least, is we're going to see that a lot here. And then it's the delocalization of electrons, meaning that electrons that could make up that bond, that could make up a chemical bond, can actually be spread out across, more than just one space. And so you don't have to write this down, because we've already talked about it briefly. But I mentioned before about how there's this, for example, here. Right? There's this thing here. And I used the nitrite ion last time, but I'm just using this since, this is organic chem, is that when you have this type of cation, or carbocation as we call it, that this isn't the only way to draw this. You can, in fact, move the double bond such that you would have this form here. And so, what I mean by move the double bond, what I mean is this, is that technically, these electrons can go over here to satisfy that charge there, thus resulting in this over here. And then we don't draw it, and we'll see this here in a second, but we don't usually draw it going the other way. We just know that both are happening. Does that make sense? Okay, so that's that. Now, and then of course, as you may remember from Gen Chem, that these, if you're wondering which picture is correct, the left or the right one, the answer is neither. It's actually a hybrid of the two. And so how some draw it is that you don't draw either of these, but rather, well, you're going to draw both of those, but technically the way it's going to look is that it's not a double, well, you can't see it, it's not a double bond and a single bond, it's rather it's 1.5 bonds spread out across the entirety of the whole thing with some partial positive charges there hanging out in the corner. So that was what we talked about last time, but now I want to get into it. So Klein, the way that he wants you to learn these, and it's not really a bad idea, I just want to, there's some caveats as one would expect with anything in here, is that one of the easier ways to tell how resonance forms or how the electrons flow in resonance forms is by drawing curved arrows. Now, the reason I have to say a caveat to this is that we're going to see these curved arrows used later on when we start talking about reactions. They're used slightly differently because, well, I don't want to spoil you. We'll just get to that when it becomes relevant again. But whenever you show curved arrows, right? When you show curved arrows in here, that is implying, or that is showing which way the electrons move, or it shows electron flow, depending on what you read. So what we're saying here, with that orange arrow, is that those electrons going from the tail, right, going from the tail, and they're flowing, and they're going to the direction of where the head of the arrow is going. So that's why the double bond that was in the left now slides over to the right. You'll see plenty of instances where it's similar like that. How are we doing? Right, so that shouldn't be a big deal. But now, how do we do that? Because, of course, I just happen to draw it like this, but I know when we start getting to more extravagant molecules, and we have to show resonance forms, how do I know where to move things? Because, of course, you can move, you in theory can move a lot of things at any time. Whenever you're drawing curved arrows, your book mentions that there's two things you need to keep in mind when drawing curved arrows. When drawing curved arrows, the first thing is you want to avoid breaking single bonds when possible. And the second one Okay. Let's see, did I get that all in there? Let me pin it up slightly. Yeah, that's good. We'll just go with that. Right, so you want to make sure to avoid breaking single bonds when possible. And for the second row elements, most notably, carbon, nitrogen, oxygen, and fluorine, you do not want to violate those octet rules. Because again, as I mentioned before, those second row elements, they can't have an expanded octet. It doesn't start till the third row. Okay. So, I guess really the easiest way to do this is to kind of go through some examples or much else. I'm trying to think. I'm looking in the book here to see if there's anything worth grabbing other than what I've already mentioned. Not really. I guess, yeah, as we'll see here, there are a couple of examples that mostly in order for this to work is that when we're drawing these resonance forms, what's going to be moving or the type of electrons are going to be moving usually are either lone pairs or double bonds. Okay, like I said, for what you need to know, single bonds that doesn't really happen, at least when we're talking about resonance forms. We'll see that later when we start doing reactions, but that, again, different context. Also, as you'll see, you notice how up top, one little thing to note here, is that you notice how up top, one of the ways that you can tell that you'll have a resonance form, or you'll know you'll have a resonance form, is if I have, usually if you'll have some sort of, either you'll have something that has a formal charge on it, on that atom, or a lone pair next to a double bond. You'll see that quite a bit. I'm not saying that always happens, it just tends to be a trend. There's at least for what you need, not only, for what you need to know at the moment, the only time when that won't happen is if you have this, because this does happen quite a bit, is if you have a carbonyl. Glad that my allergies are running amok now, that they have to do it now. So that's a carbonyl, for example. And what could happen, is that the electrons that make up the double bond can actually go up to the oxygen to form this. And so that's another way you can show that, is that you can actually show that the carbon and oxygen have a positive and negative charge respectively, and then from there, you can go ahead and make other resonance forms, and we'll show that. Like I said, we'll get to that in just one thing at a time here. I'm trying not to get too ahead of myself. Yes?
So what happened there, the double bonds broke, right? Like you just removed one of the bonds?
The first part of your question made sense, and the rest of it didn't in my head. Can you just repeat the whole thing?
Yeah, like so when you change like the resonance structure to like the partial and negative charge of the oxygen, it's because you lost the bond.
Yeah, so what happened there is, I'm breaking apart a double bond, not a single bond, so it still holds with the rules that I've mentioned here. And yes, it's the electrons that make up that second bond went up into that oxygen. Now again, as we said before, we talked about last time, at least me, I'm going to stop drawing these for the most part until, unless absolutely needed. Remember that there are lone pairs there. And so what happens is that the electrons go up, and now what had two lone pairs now had three. And the carbon is missing now its electrons. How are we doing? Right? Okay. So let's do a couple practice problems here just to kind of see if we're okay with this. And then actually, let's make this easier for everybody. If you don't want to write this down, you don't have to, because it's just easier for me to use the book instead of me having to write this all out. We're going to look at, on page 57, it's practice problem 212. And this is what I mean, because the question itself is fairly simple, because what it's asking here is, okay, so here we have 212. The question is, in each of the following cases, determine whether the curved arrow violates either of the two rules described before. And so you got to draw on these to kind of give you the answer, and it's, pick the error if need be. So for example, for A, notice where the electrons are moving, all right? And so when you practice this, I guess I should do at least one to kind of show you what I'm getting at here. So for how would this go, or how would you do this when you're first getting started? So we have this. This was the problem anyway. H, positive. All right, so that was the form. And what they're telling you is that we're going to move those electrons there, and then that's it. So pretty much, probably when you're getting started, what you may want to do is actually write out what the resulting thing would be. So let's do that. So if I write out the resulting thing, it would look like that. Does everyone agree with me, what I just did? Sounds tells me we're good. Now, I didn't put a formal charge on the nitrogen yet, but the whole thing is that, look at the nitrogen. Does it still have an octet? No. Well, in fact, actually, let me restate the question. Does it violate the octet?
Yeah.
It'll violate the octet because I've got 10 electrons around it, and that's not okay. So that proposed movement in the book there wouldn't be acceptable. And then just if you really want me to just really bring it around here, because technically that'll have a formal charge. That has a positive charge, which that's not a big deal. The problem is that 1, 2, 3. No, actually, well, let me backtrack. So technically, in terms of not Lewis charges, but formal charges, this is okay because it has the correct number of formal charges around it, but as already mentioned, because this violates the octet, the octet rule, that ain't happening, okay? So for A, that one's not acceptable. Do you understand how this game is played? Okay, we'll do another one together, and then I'll have you guys do one more, and then we'll just move on. So here I have this. Here's B. The problem's telling you that I'm moving that double bond. So if I'm moving that double bond, draw what the result would look like. And since the electrons moved up, the oxygen now has a negative, technically, and the carbon now has a positive. Yes.
Could we move the other double bond to the positive charge?
We could, but we're not there yet. Questions? Yeah, so you're getting ahead, which is fine. The question's technically just asking, though, for what's been proposed. Is at least this first step okay? That's all that it's asking. I meant to draw that in green too, damn it, or whatever. So this one here, though, when those electrons move around, did anything violate that octet rule? And what I mean by violate the octet rule, does anything have greater than an octet all of a sudden? No. It's true that the carbon is deficient, but it doesn't have more than 4 bonds, which is okay. You've seen that before. And the oxygen just got that lone pair, so that one's okay as well. So this one here, that's fine. That one's allowed. You understand me? Okay. Damn it. All right, we'll do one more here. C through L, give me a letter. Don't look. Hurry.
Let it be.
Sure. I draw a little bit differently than how it's in the book, but it's the same thing. Okay. I'll give you a minute. Is this okay? Is it okay?
No.
No, it's not. Yeah, no, it's not okay. Big old party foul, because what you get here, you were to draw this out. Now again, your book actually draws it out for you. You know, all of the draws out that shows the two lone pairs, shows how the hydrogen's bonded. On an exam, that probably will not happen. So there's a lot to be stuff you have to kind of remember there. But the way that would look would be this. So the problem then lies, again, while it's not shown, remember that before this whole thing started, there's technically two lone pairs on there. So that's 2, 4, 6, 8, 10. There are 10 electrons around that oxygen. That's not okay, because you can't violate the octet. And then for the sake of completion, that has a positive on it. And that has a negative. So yeah, no, this don't work. No good. Because at the oxygen violates octet. There you go. Yes.
How did you know the formal charge for the positive went on that carbon?
Oh, so the reason that you know that has to do with the fact that, well, one, I'll teach you how in a minute, but the other reason is that, remember that initially here, right? There was, there's a hydrogen there that we don't draw. So then when that moves, that hydrogen, we're drawing it the other way, but that hydrogen's still there, but now it only has 3 bonds to it, instead of the double bond and the 2 single bonds that have 4. It's now missing a bond, so it's going to have 1 less valence electron, so it gets a formal charge of +1. That's good. Anything else? All right, I saw a question on the internet here. So how do you know the lone pairs are there? So what's referencing there is the oxygen. You have to remember, and again, this is something that if you're not comfortable with, really you need to get that fixed now. Or by now I meant yesterday. So you're going to have to get that fixed ASAP, because the whole thing is you need to make sure that even though that those lone pairs aren't there, or I may not always draw them, you have to know that in order for example, for that thing on the left, in order for that oxygen to be neutral, you know that it's bonded to 3, that it has the double bond, there's 2, then there's the hydrogen, there's 3, and then you know you have the lone pairs to make up the rest of it. You understand me? Okay. I don't know why I said double bond when it's a single bond, clearly. But you've got to keep that in mind. So, again, if you're not familiar with that, and I know that, well, not unfortunately, but at least that when Klein gets you started here, he has them all written out. So if you want to at least practice looking at that, and hopefully it's one of those things that hopefully it should sink in after a while, I'm hoping, by enough practice, that, oh yeah, that needs a couple lone pairs. That has a lone pair. That has, 6 lone pairs, etc. Actually, now that I think about it, I can do you one better. Let me try this. This may work. I'm talking out loud now, so everything I'm about to say may not matter. You knew from the beginning, we told you, by we I mean me, carbon was tetravalent, nitrogen was trivalent, oxygen's divalent, the halogens and hydrogen are monovalent. Remember that story. If you don't, I just told it to you again. Let's think about that for a second. Whenever we drew Lewis structures for carbon, did we ever show any lone pairs? I'm thinking Gen Chem. No. Whenever you drew carbons, right, you always drew it like that. For nitrogen, right, think of ammonia. We knew it's trivalent, but what else was on them? What else was around that nitrogen? Always a lone pair, right? Well, I say always, but for the neutral ones. And so for oxygen, we said that it was divalent. So that means how many lone pairs does it have to have? Two. And then for halogens, how many lone pairs? I don't know if that helps anybody, but some of you who love doing the old trend looking, you notice that the thing that's trivalent has a lone pair. The thing that is divalent, don't get too excited. The thing that's divalent's got 2 lone pairs. The thing that's monovalent has 3 lone pairs to satisfy that octet. So again, this is only though for neutral species. If it has a charge on it, then all bets are off. But at least for getting you guys started with this, if you're not comfortable with it yet. How are we doing? Is this okay? All right, I hope I didn't confuse you. If I did, let me know and then I'll say it again, but without as many words. So, as mentioned earlier, when your classmates brought up the whole, could I move something around a bit? And I believe I already forgot which one you said before. It was that, okay. So, we said that for this one here. We talked about how originally I said that, or originally what was proposed was this. Right? And then what was asked was, well, hey, where's mine? Oh, there it is. What was asked was, hey, could we do this? To satisfy that positive charge? The short answer is yes. Because, as we'll soon see, when you're drawing resonance forms, sometimes it may require more than one error. And so that's what we have. Oops, there we go. So the answer is yes, you can have more than one error there. How are we doing? And then also, as your book does mention as well, I'm not just going to pull this example from the book, just so we all can understand this, is that when you have, it's like, and actually I'm glad we're doing this because actually we're going to look at this, another example, or not example, what's the word, situation. And that right here, you know that there's a lone pair there. Now again, like I mentioned before, because I have you notice that there's a lone pair, and then next to it is that double bond, what could happen is that, yes, that lone pair could go here to form a double bond. Now, upon forming the double bond, though, you notice immediately, wait a minute, that carbon clearly violates the octet, or putting electrons there violate the octet. However, this is now where the second bond comes in, or how the second error works, is that those electrons that make up the pi bond can slide right here to the carbon itself. Because then what you'll get is this. So again, like I said, this is just going to take some practice. We're going to do some here, hopefully here soon, because right now it's just all, it seems to be more pattern recognition than anything else. But yeah. So that's what I'm saying, that especially when you have like when you ever have like a neutral molecule, most of the time you will have to do more than one arrow movement in order to show the proper resonance form. How are we doing? Go!
Why did the second bond turn into a lone pair instead of a double bond? If the second double bond is moving away.
Oh, okay, yeah, that's a good question. So the question was, why did that double bond, that second double, or the double bond that broke there, turn into just a lone pair? The answer to that is simply that if we left it as a double bond, or we moved the double bond, we violate the octet rule. Because the problem becomes, if it were to move as a double bond, I'll just draw what you're proposing, at least I think it's what you're proposing. You're saying why it can't be something like that? So the problem there becomes that this right here technically has 5 bonds on it. And that's not okay. That's the reason. So that's a good question, though. Did I answer your asking? Yeah. Anything else? That's good. Okay. And so asked earlier was the whole being able to determine the formal charges on these resonance forms. And so with that, I'd say it's relatively simple. It's just a matter, it really is, again, in order for you to be able to determine formal charges, like I said before, not only do you need to be mindful of the lone pairs that are currently present, but also the hydrogens that are there as well. Question?
I'm just making sure the 2 lines of the ends on the right side, those are H's, not carbons, like attached to the end, right?
Wait, which ones?
Like,
The ones on the left?
yeah, like on the left, like this one.
Yeah, the one that's drawn technically here, they're technically carbons. But if there were hydrogens, I'd still have to draw them out.
Oh, okay.
Yeah. Yeah, you can't just draw an N. I know what you're saying. You can't just draw like an N. Like that and assume that there are hydrogens on it. Because that's a nitrogen and not a carbon, you do have to literally, if you wanted to say hydrogen, you would have to draw those out.
Okay.
Everyone with me there? That's not what this is. That's not what this is. Because I drew up those 2 lines, that means they were carbons. I'm just saying in general, you can't have a heteroatom, you can't have an N and O or a halogen halogens won't matter, but you can't have an N or an O sticking out there and thinking, oh yeah, there's hydrogens attached with that. No, it has to be drawn out. You have to write those out. The only time you can get away with cheating is only when you're doing the line bond structure with reference to carbon. Because yes, even though what he was asking there was about these, understand, are there hydrogens? Is there hydrogens right there?
Yes.
How many?
3.
How you know that?
Because carbon has 4 bonds.
Yeah, that's it. So even though that they're not implied, even though that they're not explicit, clearly there are hydrogens there. You just never draw them out. Not on the carbon, but for anything else that's not carbon, you have to. Oh, that's good. Whoops. How are we doing? Okay. So we're going to get a little more practice here with the resonance. And so what this question's asking is not so much to identify the error if there is one, rather, now we want you to actually draw it. Like, draw the result. And again, and it's not a bad thing. It's definitely Klein is, weaning you into this, which is not bad, because I can understand, especially when you guys first start with this. It's just like when you first start with Lewis structures, you guys, not you, the collective you, want to draw arrows everywhere. You want to turn everything into a resonance structure when it's not needed. Okay, so 215 on page 69, nice. I'm not doing A because we've already done A several times already. Let's just look at B. So here I have this thing here, this cute little bugger. The problem's telling you that there is a lone pair, an extra lone pair on the carbon that's going to collapse down to this bond here, whereas the double bond there is going to migrate to the end. So what's the result? So remember, if you follow the logic, especially now, so we talk a little more detail about this, if you follow the logic, if I see the head of an arrow going to the middle of a line, that's going to form a bond. Whereas if you have electrons moving to a point, then it's just going to stay at that one, in that one spot. Usually as a lone pair. So what I'm saying was, so when it moves, it forms that right there, so that's the result of that negative moving over. And then the bond slides to the end, and so that gets a lone pair, so then it'll have a negative. Again, there are lone pairs there, but I'm not drawing them. Yes?
Does it matter if the arrows are drawn like underneath?
No. Yeah, it doesn't matter. So what he's asking is this. I just happen to copy from the book, but like when you guys have to do this, is this a bad thing if instead of, so how I draw, you can't see because I have to turn this sideways, otherwise it looks terrible. But instead of drawing them over, could I have done this instead? Could I have done that instead? The answer is yes. Doesn't matter. As long as you're clearly showing where the arrows are moving, whether you have them drawn up or below or around, whatever, don't matter. It's okay. Anything else? Right. Okay. Do one more here. Pick a fun one, I guess. Yeah, that looks good. I'll give you a second to, if you don't have the book in front of you, then give you a quick second to copy that down. It's what's called nitrobenzene. Anyway, the book tells you, or the way that the arrows are being proposed if they move, here, here, and here. Go ahead and draw the result. Draw the resulting resonance form, and don't forget to include resonance forms, or not resonance, formal charges where needed. That's like a breather. Okay. So what it should, at least before the formal charges, look and see how everything moved around. Okay, so first off, it looks like the double bond here slid over, so that would result in that movement there. Then the double bond that's here slid up to form what looks like a carbon-nitrogen double bond. We have that. And then the double bond on that oxygen slid over, and so now there's going to be extra electrons on the oxygen. And the one on the left didn't do anything, so we're going to leave that as is. So, at least skeletally speaking, or structurally, it should look something like that. Are there any questions there? We're okay with that. Where are my formal charges? Well, yes,
If nitrogen is trivalent, why is it making 4 bonds here?
it's trivalent if it's neutral.
Oh, okay.
So for this one, could you do it in 3 separate resonance structures, or would you just do one with 3 arrows?
For this one, no, for this one it would have to be one with 3. It would have to be one with 3 arrows.
And this would go with the rule of a lone pair with a single bond.
So what happens? Well, yeah, at the very end, yes.
So what, I guess, like, what is applied to this? Does that make sense?
Yeah, I get you. So here's the thing. So the reason why we're, unlike before, where we can only move 1 or we have to move 2. Why is it that we're moving 3? Well, really, this one here is more, in my opinion, an extension of this one. In that, what happened was if we just moved 1 arrow at a time. Here's the problem. If we moved 1 arrow at a time.
You get 2 double bonds next to each other.
I think you just said it. What now?
You get 2 double bonds next to each other.
Yeah, the problem is that you start violating the octet rule, like an absurd amount. So if I were to just say move the 1 arrow, I'm too lazy, I'm not going to write that out for the moment. But if you move that 1, what you're going to get is this. So you see how there's the 2 double bonds next to each other? And then right there, as already mentioned, that means there's 5 bonds here,
Disgusting.
which, as you know, is a party foul, so that's not okay.
Oh, that's why you're moving all at once.
Yeah, so that doesn't work. So therefore, this bond has to move up to form this, and then that trickle effect happens. Because if we were to just, so let's say we only move 2 of the arrows. If we only move 2 of the arrows, that and that. Is that right? Yeah, that's right. If I just move 2 of the arrows, then the problem becomes right here. Well, not at the line, idiot. Let's try that again. Right there. So now I have 5 bonds on that nitrogen. Again, that's party foul. So because of that, that's why we have to move, and that's why at the end we have to move that last one to the oxygen. Or the last pi bond electrons to the oxygen. How are we doing?
Good.
Dr. Green one.
Then I put negatives at the oxygens and then a positive at the bottom carbon.
Yeah, so the good news is, at least for the 2 that were originally started, those technically don't change. But because now we moved electrons from the double bond into the atom itself, it now gains the nitrogen, Jesus Christ. It gains a negative. And then what was the last one you just said?
Oh, I said I put a positive at the bottom carbon.
Good, because you're right. Because you notice how here, we have a double bond here that just slid over to move the double bond there. What happened to the, remember, bonds don't magically appear, is that, oh, well now all of a sudden this became deficient, so that gets positive. So we got this hideous thing. But it's right. And that's what matters. How are we doing? Why do you tell me that now? I'm really glad you told me that now. Hopefully that'll be true in a couple of weeks. Okay, now the fun part. I've been alluding to this, now I can just go ahead and talk about it. Determining resonance forms via pattern recognition. What is this? Hold on. Oh, question was, why did I put a formal charge at the bottom? The reason is, again, we don't draw it, but here, there's a hydrogen here. So right now, that hydrogen, with the hydrogen, that carbon's got 4 bonds, has an octet. And so once we remove that, the hydrogen's still there. However, maybe hard to tell, but now we only have 3 bonds. So because now this thing has 1 less bond than it did before, it's going to have a positive charge, or formal charge. You don't have to redraw it. I'm just redrawing it because I mucked up the one where I put the hydrogen. So. Right. Okay. So for pattern recognition, the way that your book tells you is that there are some things you can always be on the lookout for, and knowing that you'll form a resonance form. All right, so let me at least put emphasis on this. All right, so we're talking about pattern recognition. Damn it. There we go. Here's what we have. And I'll just list them all first, and then I'll just talk about them. And so what's meant by this pattern recognition is what we're saying here is, if you see the following characteristics in a structure, be suspicious that it may have a resonance form associated. So in a allylic lone pair,
Do you mean that it might have a resonance structure?
yeah, what did I say?
I just wanted to clarify.
Oh, yeah, okay. I thought I said something different because that happens. Yeah, so if it has an allylic carbocation, a lone pair that's adjacent to a positive carbon, a pi bond between 2 atoms of differing electronegativity. So I don't know if you can tell that second thing there, it's the Greek letter pi. And 5. Conjugated pi bonds in a ring. So there's definitely a lot to unpack here because there's a lot of things I just have to talk about. Or just giving you the answer first, and then we're going to get into the details. So an allylic lone pair, an allylic carbocation, a lone pair that's adjacent to a positive carbon, or a carbon with a positive formal charge, A pi bond between two atoms of differing electronegativity and conjugated pi bonds in a ring. Okay, let's break all that down. In no order of importance here, but we got to talk about a few things first, because I think I've mentioned them loosely, but I think really the terms that may be an issue that are new here, I'm guessing, I believe are allylic. I mentioned it briefly, but we haven't I didn't ever talk about it in earnest. Carbocation and what needs to be conjugated. Okay, so for the first two, really, we're talking about allylic positions. So this is unfortunately some of those, like, do I just have to know this kind of thing? Yes. Not much in the way of, I'm not 100% sure of the origin of the vernacular, but it's what it is. So whenever you have a double bond, right? Whenever you have a double bond here, let's do this, hold on. Okay, just draw this. So let's just say I have this alkene here, right? Just generic alkene. And so just for terminologies here, let's make sure we understand that whenever you're looking at a position that's directly bonded to the double bond, what that's called is what's called a vinylic position. So for example, if I have, let's say, I don't know, we just have a hydrogen here, right? Since it's coming directly off of that double bond, that's an example of a vinylic position. Or a vinyl, V-I-N-Y-L. Yes. What is what? So vinylic is saying that if we're looking at any position directly off of a double bond, it's vinylic. Now, if I'm looking at a position that is one atom away, that is allylic. So again, for the sake of completion, so just for consistency, let's just call that hydrogen, so that's also vinylic. But then if I'm going to look, let's say if I'm looking at one of the hydrogens that are here, if we're looking at this spot, because since that spot is one atom away, I'm going to be drawing this thing in a problem. But that's allylic.
It means that it's bonded to like an atom in a single bond, or
I'm sorry?
so allylic means it's bonded to an atom that has a single bond.
Yeah, it has to. Yeah, it's a single bond, and it's one atom away from the double bond. So I don't know. I try to be fancy here. This nonsense isn't going to work. So I guess it's just probably better to do this. So if I have something that's a double bond, right? If it's immediately off of it, so anything that comes off of this spot is vinylic. And then anything that comes off of this spot, which is one carbon away from the double bond, that's allylic. You also can't see it, now you can. Sorry, I tried to be fancy, but none of that worked.
Is that just for single bonded elements?
What do you
Or,
mean?
like, can you put an N there, like a nitrogen, and still call it vinylic?
How do I want to word this? The nitrogen, no, it has to do with whatever comes off of it. So, again, what I'm saying is like so it's anything that comes off of this carbon. Okay, so the carbon itself isn't, but it's if there any sort of anything that comes directly off of it when we're looking at it from this perspective, it's vinylic. Whereas if it's coming off of the atom next door, then it's allylic. What I'm trying to say anyway. Hmm?
So, the Vinlic, I'm just restating what you said, I guess, is the one attached right to the carbon double bond, correct?
Yeah, it's anything that's directly attached to the carbon double bond, yes.
So what's the difference with the two drawings that you have? Oh. Never mind.
That feeling when you ask a question, when someone gets asked you a question and you don't have to answer it. That's the dream right there. That is the dream. So go.
In the textbook, it's showing like the two carbons themselves being the vanillic positions.
Yeah, essentially what we're doing here is we're both drawing two things that are the same thing. So here, I try to make this easier, but I think I'm helping nobody right now, but this makes me a terrible person. Let's look at the positive charge like we talked about before. How about this? Let's just make it even more explicit. So we've talked about this already, right? Like you've seen this one before. So this right here, this is an example of what's called an allylic carbocation. Or is everyone with me there? We've gone, and I've beaten you to death with this already. Now the other form, or what I'm trying to say, is that right here, you could also have it on here as well. Directly on the carbon double bond. And this is an example of a vinylic carbocation. And so that's just what we mean by that.
So like with the first drawing, with where you have the hydrogens, is the carbon and the hydrogen vanillic then? Or
I will just go ahead. Okay, so this is actually all right. I feel terrible because now I feel like I'm talking in circles. Let me just give me a moment. Okay, so to answer your question, yes, I will say that it technically is really the carbon, and anything that comes off of that anything off of it directly is vinylic. And so to answer, so now let me retract what I said before. There was a question earlier, if I had a nitrogen, for example, would that still be considered vinylic? At the time I said no. Is that, like if I have something that looks like this or something coming off of that, is that nitrogen considered vinylic? And I guess technically the answer is yes, but it doesn't, but we don't talk about that here in Organic 1, and even in Organic 2 we don't really make much of a comment about it. But yes, that is technically a vinylic position.
How would it be a vinylic position if it's, like by definition, it's two carbon bonds, like it's a carbon double bond?
You'll learn later on that the definitions are loosely defined. I'm going to leave it at that. Yeah, I should probably leave it at that before I hurt somebody. So, at least for right now, know that anything that's directly onto a double bond, and usually for when we talk about this, we're talking about carbon, that it's vinylic. Anything adjacent to it would be allylic. How we doing? I thought I saw a hand shoot up in the back. No, is the answer. Okay, I'm really sorry. Are we okay? Is this straightening out? I hope. Oh God, please. I hope. If it wasn't, would you tell me later? Please. Losing all my credibility. All I'm doing. Right. Okay. And so what we're saying, so that's just when we're talking about allylic and vinylic. And carbocation, I talked about it loosely, but we'll talk about it now, because even though that we've seen formal charges, positives and negatives on many different atoms, since we're talking about, so this is of course organic chemistry, we're going to spend a lot of our time talking about carbon, in that whenever you've got a positive formal charge on a carbon, we call it, hence the term, a carbocation, a carbon that has a cation on it, right? Whereas if it had a negative on it, then we call that it's a carbon with an anion, or carbanion, or carboanion. Like I said, there's carbocation, like you said there. And then if I had this, that's an allylic carbanion. So it's not technically carboanion because you can't have two vowels next to each other. It's a allylic carbanion. And then this right here is a vinylic carbanion. Okay? That's just the terminologies there. Okay. Good to go? Yes?
The carbo and the carbanion apply at the same time.
I'm just showing for the sake of name. If you're asking like, is an allylic carbanion the same thing as an allylic carbocation in terms of placement? Yes. But much later, we're going to talk about one of them's more stable than the other because reasons, and we're not there yet. Yes?
As of now, does the rules for the carbocation in pattern recognition apply to carbon ions too?
They could, yes, but I'm not quite sure, because it's been a while since I haven't read this in a couple of days, so I don't remember what happens next, but for carbanion, it could in theory also have the carbanions, you're just going to see the carbocations more often. I'm just doing this for the sake of getting y'all used to the definitions. Someone needs to update their computer. How are we doing? All right. Now, so that was that there. And then the second thing where they talked about so that's talking about that. And so when you see something like that, be suspicious there are resonance forms, whether it's with, as you've already seen, whether it's something that has whether it has a carbocation or has a lone pair, either can be susceptible. As also we've talked about in the previous example, or one of the previous examples about how if I have a pi bond next to a positive carbon, that can cause a resonance form to show. And on this same example, if you have notice how there's this pi bond with two different electron negativities, right? The carbon and the oxygen. It could show, the way we could show it is that bond could break to give you the carbon-oxygen positive negative charge like so. And the last one that we haven't talked about yet is conjugated pi bonds in a ring. So this one here is just saying that if you happen to have, they always use benzene for this. And for this last one, they're saying that if you happen to have this, now, I got to be careful with how I say conjugated because I don't want you to fall into the trap of what a lot of kids think. Yeah, I am not saying what the book says for that. So, when we're talking about conjugated, as you'll notice, it always seems to look like it's kind of this alternating double single bond thing. So for don't draw this, but so we're saying that's conjugated. This also is conjugated, where see how there's double, single, double, that whole bit. Technically, when something is conjugated, something that is technically conjugated is something that has an unhybridized p orbital at every atom. That's technically what it is. But the pattern's most recognizable in that whenever you have, if you have unhybridized p orbitals, or sorry, as your book calls it, pi bonds separated by single bonds, which I don't like. But anyway, that's just kind of the general pattern there. And so when you see something, I don't care about this one so much right now because I'm not going to talk about it, but when you have something that looks like this, right? So this is conjugated, and that every atom has an unhybridized p orbital. Does anyone not see that? So everyone sees that. You don't. Okay, very well. So, because remember, and how do I know that, by the way? So how do I know that that's really a thing? What's the hybridization of every one of those carbons? sp2, right? So all those carbons are sp2, meaning that there's an unhybridized p orbital in all of them, right? So if we were to draw that out using, orbitals, what this would look like technically would be this. It's kind of hard to see here, but you see what I'm saying is that there's p orbitals all the way around. And so that's what we mean when something's conjugated. With me there. Okay. So back to the original point is that if you have something that's conjugated, in this case benzene, all of the lines, or all of the pi bonds can, if you will, shift and can in theory look like that, and they can go back and forth. And that's why actually sometimes when you look in other books, when we talk about this particular structure, a lot of the times what you'll see is instead of seeing the alternating double single bond pattern, a lot of times you'll just see that, put a circle. It means the same thing. How we doing? Yeah.
If you take off a double bond, it would still be conjugated anyway, correct?
If you take off a double bond, will it still be conjugated? Only a portion of it will be.
Okay.
So what you're saying, yeah, I know what you're saying. So here, I'm telling you for this structure, the whole thing is conjugated. But what if it looked like this instead? What if I just have something that looks like that? Technically, this is the only part that's conjugated, not the whole thing. Because of reasons. Yes?
So, I'm confused, but I'm not exactly sure where of the entire situation. I'm confused.
That's the best part of confused.
You talked about, it has an unhybridized p orbital.
Yeah.
How can I recognize that? Because I'm not seeing it. I'm a little confused on
Are you telling me you cannot see three-dimensional shapes from two-dimensional pictures?
I can't.
How dare you?
I know.
This is what makes you a terrible person. That's fine. That's like the big problem for them. I don't really. I get you. I'm just joshing, or whatever the kids say these days. I don't know. So let me actually answer your question for realsies. So here's the thing. You remember from Gen Chem, right, when you talked about hybridization of orbitals. You had sp3, sp2, and sp. There's other flavors. I don't care about the Ds. We're not caring about the D today. So sp3, sp2, and sp. So if I have something... I'm not saying we're never caring about the D. It's not today. Your mind's out of the goddamn gutter. So, when you have something that's sp3 hybridized, we're saying that that central atom, all the bonds are sp3 hybridized, right? No, and everything's hybridized, no if, ands, or buts about it. When you have sp2, though, right? When you have sp2, we know that only 3 of those orbitals are hybridized, but that still means there's one unhybridized p orbital. Now, if you're wondering where does this come from, all right, let's backtrack to Gen Chem. It all comes back to Gen Chem. So this is, that's an orbital diagram for carbon, okay, for the valence electrons for carbon. Everyone with me there. Now what we're saying is, remember what hybridization is that I'm taking these orbitals that are of different energies, right, they're different energies, and what I'm doing is I'm going to do some sort of magic, which is called hybridization. But for what you're asking about sp2, I'm going to take those 3 orbitals, the ones that I squared off, I'm going to hybridize them. And so what I get 3 orbitals. So if I combine one s and 2 p's, all of these are sp squared hybrids, right? Everyone with me there? Are you good? What do you mean this?
I'm just confused because I was practicing hybridization yesterday and I drilled in my head that carbon's always sp3, so now I'm trying to understand, like, why is it not?
Okay. Okay, and I'll get to you. Okay. So, it's always sp3 when it has 4 bonds. 4 bonds. If it only has 3 bonds, as in, what am I doing? I can draw things. Jesus. That. Hybridization is sp3. If it has 3 bonds, like that for example, sp2. If it has 2 bonds, sp. We good? Okay, so at least if you understand that, that's good. That's a good start. Now, back to what I was saying up here, is that if you have something that hybridizes into your sp squares, notice how I didn't draw in all the lines, right? I didn't box all of them in. What's up here? Poor unhybridized p orbital hanging out by itself. And so that's why when you drew those orbitals for like sp squared, you always drew them like this, so you had that trigonal planar feature. But remember what's still there is there's this unhybridized p orbital hanging out. And remember, when you were first learning this in Gen Chem, it was those unhybridized p orbitals on 2 sp squareds that gave you the double bond. That's what made the pi bond. It was 2 unhybridized p orbitals overlapping. That make sense?
Yeah.
A little bit better than just this?
Yes.
All right.
In the benzene, where is that, like, I don't know how to explain. So is the double bonds like the ones that are the unhybridized ones?
Yeah, whenever you're looking at a double bond, right? Anytime you see this, like, because I think we're all familiar with a P to P overlap, right? Pi to pi overlap, where you have those vertical bubbles looking like this, and then they tend to blend into each other. That's the unhybridized p orbital that I've been mentioning this entire time. But no, that's good. How are we doing?
Better, thank you.
Go.
I've been just like reviewing because I got to Chem 1B a year ago. So like when you do the sp hybridization, you're putting the electrons from the s orbital into the p orbitals to like complete the outermost shell, right?
Yeah, they're only going to the valence. We're not talking about the core. There's technically a 1s electrons as well, but they're core, so we don't care. And remember that when we're talking about, this whole bit here, the only reason we have hybridization, it was to give us an explanation as to why is it that a bond angle for sp3 is 109. Why was the bond angle for sp2 120, etc. The reason we couldn't come up with the explanations we had at the time with valence bond theory, it just wouldn't work because we all thought everything was 90 because everything looked like a 3-dimensional graph. That's when the whole concept of hybridization came in and really helped modify valence bond theory to what we know it as now with this hybridization nonsense. So this is just really an explanation of what we've observed. That's another hand shoot up.
So,
Go.
So if,
Sorry.
if you have like a carbon that's sp3 hybridized, then it's not going to be continuity because it's going to
Depends.
like if you have like the ring. Like,
I know what you're asking. The answer is depends.
on what?
Lone pair.
that's what I was going to ask. If we have a carbon with 3 bonds and a lone pair, is it still sp3?
Depends. answer your question, when it comes to the ring, yes. When it comes to the rings, they're more locked in that those things on the, well, whatever I drew, like those two things that I drew over there is SP3. Like those are clearly SP3, and that means they're not part of the conjugation, yes. Spoilers. Don't write this down. If you're thinking about being confused, what I'm about to say, just turn your brain off for about 3 seconds. The hybridization of this thing's SP squared, right? The hybridization of this right here is SP cubed or SP squared, depending upon the situation. It's like, you know how Y reasons. Let me give you a poor analogy. You remember property of light, right? What's interesting about light? It could be a wave or it could be a particle, right? Remember, you may have heard that wave-particle duality thing. If you've ever wondered, well, which one's actually correct? Is light as a wave or light as a particle? The answer is yes. It's whatever you want it to be. Whatever makes it easier for you to explain whatever you're trying to explain. Does that make sense? So if you believe that, which I know is kind of hard because it was quantum mechanics and I know how that usually goes in Gen Chem, but note about that, if you understand wave-particle duality and accept that, it's kind of this situation, not to as an abstract case, but when we have a lone pair on something that's sp3 hybridized, it has a little bit of bend to it. Because it's not a bond, it's a lone pair. Remember what a lone pair is, it's just electrons hanging out, not doing anything. So because it's not bonded to anything, it has the ability to fluctuate and shape a little bit.
So would it depend if it's like delocalized or localized?
No. It's one of those things, actually, let me backtrack. If you have something that is sp3 hybridized, that has a lone pair on it, and it's conjugated to something, right? It's next to a double bond, or can resonance delocalize, it can shift to sp2. Whereas other times it can stay as sp3. Now, don't get hung up on that, because what we're talking, really this conversation now, we're going kind of beyond it, not beyond the scope, but beyond this particular section at the moment, and that's just talking about that with anything. What makes any subject more difficult as you go along, you start learning the exceptions. Now you're learning the exceptions. You're learning the nuance. Nuance is always a hard thing to learn when you first hear it because you've never seen this before. And that's okay. But don't get hung up on that. Right now, what I want you to focus on more so is if I give you something, right? If I give you something and I ask you, draw me resonance forms. You should be able to do it. That's what I want you to get out of that. What we're talking about is down the road once you become more comfortable with this. We okay?
So ultimately the continuity is just alternating single and double bond.
You just want to be careful who you say that to. I know some colleagues of mine who get upset when you say it like that. That's all. So here I have this. It's the last thing, because I know we're almost out of time. So here we got this, right? So let me walk you through it. Again, the way this works is that, look at what we have. The thing that I've observed here is the fact that, okay, clearly I see a carbocation next to a double bond, right? Next to that alkene. So what I would expect one form of this would happen would be this would move here to satisfy that carbocation charge. So what we have is this. And so again, remember why that happens. It has to do with the fact that because the electrons in this center part here shifted over, that means now this one becomes electron deficient. How are we doing? And because that's electron deficient, and there's a double bond next to it, this can happen again. And so the end result is that you have all of those right there. And likewise, the electrons can shift back to make the compound, or to make the structure on the left, and you get the idea. How are we doing? Okay. So, what I'll do next week is we'll do a couple more of these problems. By the way, if you don't know where this came from, this was on page 75. This was page 75, question 225. I just did B, but there are others there. Do those. And then what we'll talk about next week is talking about the differences with residence, like which residence circuits are more important, and then I'm going to start chapter 3.